Theorem 8.55, and it says if I have a nilpotent linear transformation from V to V, then there exist vectors V1 to Vn. N is the dimension of V. No, n is not the dimension of V. Sorry. From V1 to Vn, and non-negative integers m1 to mn, such that this list is the basis for V. And if I add 1 to the mi's and then raise n to that power, and input the corresponding Vi, I'm going to get 0. So this is what the statement says. And now we're going to prove the statement. If you look at this statement, there's like no intuition, and you don't really know how to approach it. But then you see I'm proving a general statement about some number n, and then you're like, well, maybe this looks like induction, and that's exactly what we're gonna use. Now we need to decide what we're inducting on. Well, the obvious choice is the dimension of V, and that's what we're going to use. And it also doesn't make sense for the dimension of V to be negative. So we're starting with 1, because 0 is like nothing's in there. So let's start with 1. The dimension of V is 1. Well, when this happens, there's only one basis. The basis is, there's only one thing in the basis. And now there's only one choice of what n could be, because n is a linear transformation, so it permutes the basis. There's only one basis. And if it sends that basis to the same basis, which is itself, then it's just the identity map, and it will never become the 0 map. So obviously n is the 0 map, and when n is a 0 map, and also we also know what the basis is. It's just the one vector. In this case, m is 0, and the basis is V. So now we state our inductive hypothesis. For dimension of V equal k strictly greater than 0. Oh, actually strictly greater than 1. The result holds for all I less than or equal to k. So we're using strong induction here. So we're assuming for all the integers before including k, the result holds. Now we do the inductive step. So we want to show the statement is true. Statement is true for dimension of V that is k plus 1. Okay, now we have cases. The first case is when n is just the 0 map, then we're done. Just take whatever basis that V has. It's the same argument as the base case, because I just take whatever basis V has, and then for each of the mi, it's 0. And then boom, I have a basis of V, and if I apply n to any of the basis element, I get 0 because n is a 0 map. And the other case is when n is not a 0 map. Okay, well, now we need to investigate and find out facts about n. And starting with what we know, the only thing we know is n is a nilpotent map. And nilpotent, so this means n is not injective. Because if n was injective, then, well, since it's a map from V to V, then it just permutes the bases. So it would never, like, it's just a permutation of the elements, so it doesn't matter how many times you apply n, you will never get a 0 map because it just permutes the elements. Okay, so nilpotent and it's not injective, and using a theorem from before, when we were talking about bases, I know n is not surjective, which means the dimension of the image of n is strictly less than the dimension of V. Okay, now I find out something that's valuable about n. Why is it valuable? Because, well, look, I have this strictly less than sign here, and then that suggests that I can use the inductive hypothesis because, you know, every number that comes before it, I can apply the inductive hypothesis. So that's what we're going to do now. But, like, how would I, to what map am I applying this inductive hypothesis? Because obviously the map would have to go, this map that we're applying the inductive hypothesis to would have to go from Mn to Mn. So the image Imn, the image of n to the image of n. And then, well, what maps do we have? We only have one map. So n has to be in there somehow, but then now I'm like, well, and, you know, the domain is image of n, so maybe I can restrict it to the image of n. So this is our new map, and we're going to work with this map. Let's see. Okay, so we apply the inductive hypothesis to this map, and then by the inductive hypothesis, I know that there exists V1, Vn. Well, now I'm just assuming n is the dimension of the image of n. And then Mn such that I'm just rewriting what the statement says. Oh, I'll just copy it from here. Copy. Okay, so this is a basis. And I know this is true. Okay, so this is what I have, and I'm gonna give this a name, star. Okay. Now let's investigate some more about the restriction of n to the image of n and this new basis we found. So this is basis for image of n. So we know star is the basis for image of n, which means for each of the vj in image of n, this is the vj's are in image of n. There exists a uj in V such that n uj is vj. That's just the definition. So I can rewrite that as k plus 1 uj nk vj. Okay? Now, I'm gonna claim this list that I'm gonna call flower n plus 1 u1 n u1 u1 n plus n plus 1 un n un un. I'm going to claim this is linearly independent. The reason why I do this is I can use this as a linearly independent set, and then using what we did when we were learning about basis, I can extend it to a basis for V. Okay, this is information that we need to refer to later on, so I'm gonna copy them over here. Okay, so now we have to prove this is linearly independent. Okay, as usual, we start with a linear combination of these vectors and make them 0. Okay, I'm not gonna label the C's, pretend they're labeled. C, 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 and C. And then this is 0. Now I want to show all the C's are 0. How are we gonna do that? Well, we know one fact about the UIs is this fact. So we want to somehow use this fact, and well, now when I see this fact, I'm like, well, there's U and then there's V, and what I know about V is this is the basis. It's linearly independent, so I want to use that somehow. And then, but how can I use it? Well, it says in order for U to become V, I have to apply the map to it. So that's what I'm going to do. I'm going to apply N to this entire expression. Well, on the right hand side, since N is linear, so it's 0, 0. So now I have a new expression. If I permute the n inside of the bracket and distribute the terms, I'm gonna have copy. I'm gonna have n in here, and then n in here, and then, well, I'm just rewrite the terms. C and U1, and then C n plus 1 and UN, C n and UN plus C and UN. Well, using the fact that we wanted to use, this is just V1. And then this is also V1. V1, Vn. So we can rewrite, actually we won't rewrite it, I'll just explain it verbally. So you can see this is a linear combination of this basis over here on the left hand side. Yeah? And some of these terms are 0. This term is 0 according to according to the second statement here. So whenever I have a plus 1 in the exponent, it's 0. So that's 0. This is also 0. But even though these terms are zeroed out, all the other terms are still a subset of this basis. So they're linearly independent. So all the C's here, this C, and this C, and this C, and this C, I know those C's are 0 for the highlighted the highlighted C's in red. And the last thing to prove is 0 is these C's with the exponents plus 1. Okay. So to prove these C's are also 0, we just have to like take a step back, and I'm just gonna write a linear combination of only those terms with the plus 1. It's still a linear combination. So I'm gonna write that. Because I want to show they're also linearly independent, I am gonna make this 0, and my goal is to show all of these C's are also 0. And if I take the 1 out and write in n here, this is V1. This is Vn. Look, this is again a subset of this basis on the left. And I know this subset of a basis, it's linearly independent. So all of these C's are also 0. Boom. We proved that flower is linearly independent. So now we have a linearly independent set. What we said before was we want to extend it to a basis for V. Extend flower to basis for V. We know we can do that. So I'm just gonna write down the original expression. I'll write down the original expression plus the elements that I add. It's going to be W1 up to WP. Okay, new WIs, and we're going to find out more about these WIs. First thing we try is remember when we applied n to the entire expression here. You know, it's a common trick. Let's do that here again. See what happens. So I apply n to the wj. And what do I know about this? Well, obviously, it's in the image of n. And we said before, the image of n is spanned by these vectors here. So I can write n wj as a linear combination of these vectors. I'm going to copy them. Copy, paste. Okay, I'm going to write linear combination. Again, I'm not going to index the c's. Linear combination, linear combination, dot, 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 linear combination. Okay, plus c. Okay, we wrote n of wj in terms of linear combinations of elements in star. And what we know about elements in star is they're very related to elements in flower. So we know V1 can be written as NU1, and it applies to all of these V1s. And then this can be written as NUN, also applies to all of these Vn, and it applies to any of the VIs that we write down in this linear combination. And here's something about this expression. So I'm adding an n in front of the ui's. Since n is a linear combination, I can factor out the n because, you know, linear combinations are preserved under addition and scalar multiplication. So what it means is I can factor out the n, and inside I would have this exact linear combination, but without the n. And now I see, look, the elements in list flower. Do you see? If I make this n go away, let me mark them like this. Make this n go away, it's just elements in n flower. Okay? So I can write, when I factor out the n, I can write the big expression inside. I'm not going to copy and write it again. I can write the big expression inside as an element x, and xj is in the span of flower. Okay? That is just what I just explained. And what this means is now I define, using these WIs, I'm going to define some new vectors that will satisfy the desired properties. So let's look at an easier one first, which is like this property, which is just saying if I apply n one more time and then I get 0. let's think, well, how am I gonna get 0 with the wi's, the wj's? Well, look at what we have here. How am I gonna get 0 using the wj's? Look, this is what I have, and 0 is like right there. And I can write this as wj minus xj. Boom. So this suggests that the new elements that I should write is this. So that's exactly what I'm going to define the new elements. I'm going to define this as n plus j. Why n plus j? Because look, I already have n here, and then I'm just like adding j to the index. So I define this as n plus j, and the new list I have satisfies our desired property. Okay, u n plus 1 dot 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 u n plus p. Well, obviously, all of these already satisfy the property because star satisfies the property. And if I apply n one more time to any of these elements, I'm going to get 0. Also, I also have the first property with these. And now I just need to check these. We already checked above. If I apply n one more time, then 0 times to these u of n plus j, I'm going to get 0. Okay, so that suggests for all of these u of n plus j, the m of n plus j is 0. Yeah. Because I'm applying one more iteration of n, and then I get 0. And then what's one more what is a number such that 1 is 1 more than that number? That number is 0. M of n plus j is 0. And we proved above, if I apply n to it, I'm going to get 0. So, we have our basis, and it satisfies the first requirement, which is I have some non-negative integer m, in this case, for the new ones. M of n plus j is 0, and then all the other ones, I already know they satisfy the requirement because they come from the inductive hypothesis. So if this is actually our basis, then we're done. So the last thing we need to check is that it's linearly independent and that it spans V. Okay, I already know the blue ones are linearly independent, so let's think about why the purple ones are also linearly independent. It's linearly independent because, how did I obtain the n plus j? It's wj plus xj. And, well, let's think about what xj is. Xj is in the span of flower. So, if I only look at the xj part, then it's not linearly independent. But I have this part of wj, and remember where we got wj from. Wj is from when we appended our blue list with linearly independent vectors to make a basis for V. So all of these wj's are not a linear combination of any of these blue vectors, and these blue vectors are precisely the vectors that are in that spans flower. So this is not in the span of flower. With the span of flower is these blue ones. So it's not in the span of flower, and then all the wj's are independent of each other. So we know this wj cannot come from a linear combination of anything in this list up here. It's lagging a little. Yeah, now we can see. So the wj's cannot come from a linear combination of any of these except, wj itself, but you know what I mean. Cannot come from a linear combination of combining any of these vectors in here except wj itself. So this u of n plus j is linearly independent in this list. Okay? Or to rephrase it, these u of n plus j is just we can see how it's linearly independent if we just subtract the dependent part from it, and then we get back a list with wj's above, and it's linearly independent. So this new list is also linearly independent. Okay, so we've proven that this list is linearly independent. Now we just have to show that it spans V. It spans V because it has the exact same number of elements as up here, and then they're linearly independent. And if you remember when we did bases, that means this linearly independent set also spans V because it has the exact same number of vectors as the one above. Okay, so that shows this list is indeed a basis, and it also has the form of the desired form, which I have explained before. So we're done.